Downloading mods for a video game is not safe. More often than not, the hack or the cheat or the mod itself will be malware that'll infect your computer. Or even, if you've found some mod developers or a community in a hub that shares what should be clean and trusted mods, there's always the chance that the developer and something some way along the supply chain could still be compromised. And that is part of the story that we'll talk about today. Because recently, just a little bit ago, and I'm behind on this, I'm a little late to the party, but look, on October 31st, Halloween, one member of my Discord server shares we have a malware incident in the City Skylines 2 modding community. Potentially thousands of game players affected, and there is an official post by the developers, and including a virus total report of the suspected file or the malware and malicious part of this mod. If we actually take a look at the official post that was linked, that is over on the Paradox forum, and I gotta say, I don't play City Skylines 2, I don't use any of the mods, I've honestly never heard of this Paradox forum before, but it seems like this is where a lot of players get some stuff about the game, mods, things to get in the action, and that is a well-known, trusted, and reputable source. But there is an important update for all City Skyline 2 players. There's a potential security issue that has affected the traffic mod for City Skylines 2. Late Monday evening, an outside actor pushed an update to the mod, which includes a .dll file, or a dynamic link library, that they believe is malicious. We've already removed it, and the current version is still safe to download now. But if your mod was synced and you played the game using that mod between Monday and then there's a possibility you may have had the malicious file and have been compromised or affected. In this video, we'll do some reverse engineering and malware analysis to make sense as to what this mod really did. And we'll tell the whole story. From beginning to end, from cradle to grave, we'll talk about the original infection, hearing it from the mod developer themselves, and we'll understand the whole community response. And I gotta say, there's a whole lot to this story, especially with just how the community kind of came together. Because a lot of people have been talking about this. Eric Parker was digging into this, Low Level was chatting about this, people were screaming all over Reddit. I know the PC security channel and a whole lot of others were trying to track this thing, but if I may say, and I think this is awesome, I think the ground truth really came from JH Discord, which is pretty cool. Hey, Rem, my coworker, was tagging some other sweet, smart individuals. I do want to give the shout out to Loch Ness. Loch Ness Co. has done some incredible things with this, Illuminati Fish, and all the others that did get a chance to dig into this. And I know we had like the people from the City Skylines game modding community jumping into the server, chatting, trying to understand, and it was really cool sort of synthesis of just normal game players and developers alongside like security researchers, reverse engineers, malware analysts, and there was just a really, really cool kind of, I don't know, showcase of the conversations and how that was going back and forth. And I know that I will ramble about that more later, but when we really get into this, Loch Ness over on November 1st said, okay, I'll dig into this now. And I know that Loch Ness is a big fan of Binja or Binary Ninja, because when you're doing reverse engineering, malware analysis, you've got a lot of options, right? You could be using Ghidra, you could be using IDA, maybe R2, Radar 2, however you say it, and Cutter and the graphical user interface. But I know, and even my great friends tell me, hey, Binary Ninja is pretty awesome. So we thought, look, let's follow along and do this just as well. We do have the sample over on Virus Total. Note that it has like 40 out of 72 detections across all these different engines now. And at the time recording, it's November 10th. Granted, this was all kind of breaking ground on October 31st and November 1st. So there's been some time delta here, but at least it was uploaded to VT so we could download it. Or I could download it, I know, with Virus Total Enterprise, but not everyone can. So this was shared on Malshare, and I'm thankful for that. And I do want to give a huge shout out to Monkey and Raver from the PC security channel. They had shared the sample with my video editor Nordgaren, and I do need to give an extreme amount of thank you and kudos to Nordgaren because he, if you don't know, does a heck of a lot more binary and compiled language reverse engineering than I do. In fact, he's a game modder himself and super duper qualified to dig into this. So I got to learn a couple tricks from him as we got to download this fastmath.dll and rip it apart in Binary Ninja. This is a real malware sample, so it should really be looked at inside of a virtual environment for safety and security, right? I've created just a Windows development box, and you should have a snapshot ready and snapshot all the time as often as you can when you're putting this together. I'm just using VMware Workstation, but as this virtual machine starts up, we can go ahead and get in our disassembler and debugger. And before we go too much further, please let me say this video is sponsored by Flare. I'll tell you more about them soon, but just for a super quick crash course, Flare is a threat exposure management solution. That means that you can create different identifiers and even keep track of any activity out and about on the internet or even the dark web. So whenever someone is chatting about you, your company, your business, your employees, your people, anything that you might want to add different sort of detectors for, you could see that across even anything in illicit networks like marketplaces, forum posts, ransomware blogs or leak sites, Telegram channels, and all that shady dark web stuff, or just on the open internet, like pastebin websites, leaky S3 buckets, GitHub, and more. And of course, there are a ton of data that they have available from ingested InfoStealer malware logs. This is where you could see any of the credentials that, again, you, your team, your peers, your colleagues, others that might have their information exposed out on the internet, when you could track down, even by domain, email, username, password, or even with a website that data was leaked from. There is so much more you can do with Flare between their API, setting up custom notifications or alerts when some information is found out and about, or even just taking a look at generated threat intelligence and curated CTI pertinent to you and your business and your company. Maybe you need to stay on top of what information is out and about from threat actors and adversaries and what they're doing in the current landscape. Look, you can get access and see all this and more with a free trial, link below in the video description, to get started with Flare. All right, now that we are inside of our virtual machine, we've got our fastmath.dll file downloaded and ready for us to take a look at it. It's nothing fancy here, nothing special. Taking a look at the details, security information. It is not signed. There's no certificate that comes alongside this. We can start to open it up. Now, you might do this in IDA, you might do this in Ghidra, but we, in this video, could take it on in Binary Ninja. So I'll open that up, I'll click the open button, go navigate to it, and we'll walk through everything and everything here. And it will start us in the _start function. You can see that in the very middle of the screen. We're taking a look at the display in the code view, where we actually can take a look at the raw bytes if we really wanted to, kind of much like a hex editor, but really we should get back to the portable executable, PE. Linear for how we might be able to view the code. You could of course see this in the graph view, which you might be used to in IDA or others. In the linear setup here, we actually could toggle this to the raw disassembly, where we're taking a look at just the assembly instructions, or the high, medium, or low-level intermediary language. Honestly, I really like the pseudo C code because that way it just looks like code that we might be used to seeing in pure C. You do, of course, have all these symbols on the top left. We could explore those further, cross-references to whatever we're looking at, but really what we can start on is this start function here. All right, now before we go too far though, I do want to show you this really cool view that Binary Ninja offers you. If you just go up to the view menu, they do have this triage summary that has a lot of really quick and convenient easy analysis stuff that you might be liking in malware analysis, reverse engineering, usual incident response. You've got your entropy sort of visualization here, typical file info, header information, and we can scroll to the right there to see a little bit more. But especially with this being a DLL, it's probably worthwhile to take a look at imports and exports. Now, normally, like an online sandbox, maybe AnyRun or Joe's Sandbox, hybrid analysis, whatever, they would try to kickstart and run for dynamic analysis with any exported ordinal, like run DLL, DLL.dll to call the file, and then like #1, or the first exported function. Unfortunately, this has no exports. So pretty clear, this one's a little bit sketchy. This is certainly, and we'll find more, this is malware, but it's a little bit ghoulish on the inside, and I think that's worth noting. Look, seeing kind of a sketchy, no exports DLL. Of course, we could take a look through the strings here. You can, of course, search through anything and everything if you wanted to within Binary Ninja, but there's nothing special or secret here. No easy wins. I can't just run strings and be done with it. We are going to have to do some real reverse engineering. So with that, let's get to it. Now, note this is a DLL. And that must mean that it's going to be maybe attached to or ran inside of a process or hey, whatever loads that dynamic linked library with a DLL reason as to whether it's being attached, detached, whatever. You're probably used to seeing that in the boilerplate code to create a DLL, and normally that arg2 would be the reason that is actually being worked with in this DLL. So we're checking if the arg is equal to 1, in which case we use this sub function call here, 1800C78, whatever. And if we actually double click into that, we can see a lot more of the usual boilerplate that's handling for like the security cookie. Stack canaries stuff to handle that process, so nothing all that interesting for us. We can hit N on the keyboard to rename that as the usual security cookie function. Nothing fancy, hit accept, move on. We do have the call that follows though, DLL main dispatch. If I double click into that, it is, as you would expect now, to handle the reason with the DLL that was passed in with arg1, arg2, arg3. Now inside of this function, we want to track down where the code actually happens, like when things start, right? Because if we find some logic or a code branch that goes to the end of the program or the end of code to run, well, it's not going to run, and that's not all that interesting for us. So this conditional here, if arg2 is equal to 0, and whatever data value, we could double click in, noting that's just zeros to start, presumably. If that's less than or equal to arg2, then we return 0. Nothing happens there, so that's probably not interesting. We're probably not going to find the condition where arg2 is equal to 0. We might assume when the security cookie is set up, if arg2 is equal to 1, from what we just saw before, we could see if arg2 less than 1, if we're subtracting 1 from it, is somehow suddenly then greater than 1, that would fall down this code. But that's probably not going to happen because we know maybe presumably arg2 is 1. So let's just kind of follow through with that train of thought here, thinking let's not take that if statement. If we were to do 1 minus 1 greater than 1, not going to happen. Let's hit the else statement down below. But if we do that, we set rbx to 1, which if we're checking if it's not equal to 0, which we know is now 1. So strange decompilation setup there, but that will actually tell us, okay, we call this conditional enter this rax2 will equal our DL main CRT dispatch, arg1, arg2, arg3 all being included. So we do follow through with this logic. DLL main CRT dispatch. Let's click into that and go see what that does. Oh, well, actually, taking a look at the code here, you could see a little bit more information on it either attaching, detaching, doing whatever it might do based off of arg1 or arg2 here. But that looks like regular handling for DLL. In this case, our arg2 were to be 1. If we were, again, working with that hypothesis, we do end up calling this thing sub 1800C6F whatever. We can double click into that, and then what do? Scrolling through to understand a little bit more regular startup lock, fast fail shenanigans, DLL main before initialized. That's going to end up initializing, having stuff run. This sub is just initialize slist head, nothing peculiar. Default, local, standard input and output options. Oh, and then we do something with a lot of data values here. And we could double click into these, data 1800C8 whatever, more zeros as we expand and explore them. I'm hitting escape to go back, by the way. Same thing with another, nothing all that interesting, but we do check after initialize, we use this init term function with data again, currently being zeros, and then data again, currently being zeros. But in between those two, we do see a subroutine, a sub that is really something interesting. What is that init term actually kind of doing? Because that seems to be the only thing that will happen in this conditional. Everything else is released. RDI check we'll go through with regular dispatch calls. Nothing fancy there. So that looks like the only thing that would happen if this is going to end up being returned out of the function here for our DLL CRT main dispatch, right? That function, if we go back into it, will do something with init term or init term. What is that? If we go Google init term underscore E from Microsoft documentations. Thanks, Microsoft Ignite. Internal method that walk a table of function pointers and initialize them. The first pointer is the starting location in the table. Ooh, and the second pointer is the ending location. So it's just defining bounds when we saw that init term thing, whatever. And if it's going to initialize and probably run some functions, like realistically, that means that what we just saw at the start, C8200 being the zeros above, and then just following that was the C8210 being the end. That means that in between here, this data that is a subroutine, double click on it, that's a function. Oh, wait a second. It says this function is too large to analyze. What was that? Yeah. Force analysis of this function. This may take a while. Okay, so giant bloated function, presumably. We can double click on that and we can see down on the bottom left, analysis phase 1, it is now analyzing to rip apart and see that function. Might take a little bit, so I'll pause and wait until we get there. Okay, so now that this big sub 18.000.1000 is done analyzing, we can scroll through it and it's kind of weird. Like, you see all this? There's a lot of character variables being defined. A lot of 3s randomly, like weird random stuff. Just a bunch of variables being created. A lot of 3s, a lot of 33s in hex. They just seem to be odd. And this goes on and on for a long time here. If I scroll down, this must be why that function was so big and was not analyzed automatically. But if I were to I know I'm looking at the sudo C. Let me switch this to the disassembly and, oh, hey, Binary Ninja just took a second. It's hanging there because this is probably taking so much time. A little bit of lag. I'll see when this comes back to life. Okay, yeah. It's coming back to us. But look, just everything you'd expect. Move instructions over and over and over again, adding to RSP and one new byte at a time. So presumably building out like another payload, like a second stage, and you see this hex 33 over and over and over again. Let's kind of table this for the moment. Let me bring us back to what would be the start of this function, where we could see all the move instructions start and then continue forever. But this is code, right? It will execute this and put this all on the stack. Ultimately, it's going to be loading something into memory. So let me rename this. Let me just hit N to rename this to like MW. We can add that status. Yeah. Like whatever may be right. Payload is probably a fine name. But once that's renamed, let's sort of walk backwards and kind of, hey, remind ourselves how we got to where we are. I'll hit escape to bring us back. And I do want to bring this back to sudo C so we can see some of the code. Because remember, we saw that inside of that init term sort of function between those two bounds. And that was in this subroutine that was all inside of, we could call this whatever we wanted to, but it was in the DLL main CRT dispatch. And that DLL main CRT dispatch was in the else statement of DLL main dispatch that we started with. But once we were done with that, we could see we're testing if RAX2, the return value of that, if it did not fail, right? If it's not equal to 0, then we go to this label. So I double click on that. Oh, it just brings us back up to the else statement that we started with to begin with, but whatever. Ultimately, that calls this subroutine, which calls this subroutine if R2 is equal to 1. So let's drill down to that. Oh, and what's going on here? We can check while current process ID is not equal to hex 1234. That's not likely. That's probably not going to happen because that's going to be a random process ID. That will be a true condition, so we'll enter this while loop. We can check if we can flush file buffers, and that will be the break. So assuming that's not going to happen, we keep adding to RBX in the loop, and maybe some way, somehow we'll follow through. Once RBX is greater than or equal to whatever hex value, we do something with data here, data underscore 1800, and this is memory that we could click into and take a look at. So it starts at 0, you can see that. And that's, I'm going to assume, an iterator, right? Because we have a do while loop here, but they do something interesting. They have an I null pointer where they're sort of doing like an inverse index into a buffer, presumably, because they keep growing and adding this over and over and over again. But that's a different data value because the other one was ending in CA750. This ends in CA758. So double clicking on that, It starts as zeros, presumably, but this loop will XOR. Oh, XOR, you can see the clear as day, right? This line here, the caret symbol will XOR with hex 33, which is just what we saw when we got to see that other big subroutine function, and a lot of those 333 hex 33. So I'm curious, is that all the move instructions that we saw is just a second stage payload XOR'd with hex 33? We could probably take a look at that. We could extract that dynamically, but just to like go check, at the very, very top here, the symbols, we did rename that to whatever payload. If I double click in here and go see this one more time in the disassembly, take a look at these move instructions, right? We start with hex 7E and then 69. So let me open up like Firefox. This can be super simple, super dumb and easy. Like, let me just get genuinely CyberChef open. And then literally 7E69, that is hex, right? So we need to do from hex. And then we can say XOR with the key being hex as the option set, 33. The output is MZ, the very start of a portable executable header or executable.exe or .dll, right? So that whole subroutine, everything that we're seeing here is probably just another second stage payload XOR'd with hex 33. Let's extract that all out dynamically with a debugger. If I get back to the section that we were in when we saw this XOR operation, we could just add a breakpoint after that do while loop. Honestly, we could just hit F2 and you can use a debugger here within Binary Ninja. But I'll admit, I don't know. I've seen that do, I don't know how to set that up smartly with a DLL or dynamic link library. I do know that x64 debug, another debugger that so many people love, can handle that really nice and easily. It'll just use like its own internal DLL main to get smart and do that. So let me do that with x64 debug. Before we do run that dynamically though, we know and need to understand that, okay, running the process will put memory locations in different spots that will be different than what we would see in Binary Ninja, right? All because of ASLR, the address space layout randomization. So what we can do is actually open up the 010 editor, and I gotta give huge props, big shout out and big thanks to Nord Garen because he's taught me this. If we were to try and open up the fastmath.dll, that will actually tell us, look, you could use this template because they do have some smart understanding of what all these different file formats are to make the 010 editor a super smart and good hex editor. We can install that super easily. And now it'll know, okay, these are all these sections and headers and things that are important for the file that you're actually looking at. So I can drill down into, just down below here, the NT header, I believe, and the optional headers here. Going to the very, very bottom of this, we should be able to see what would be the DLL characteristics. Taking a look in that, we can go find, if I expand this out, the dynamic base. And that is what will allow us to, if I toggle this 1 to a 0, change this so we don't have the ASLR in action for this binary. I can hit 0 and then save, Control S. Now, when I open up our x64 debugger, and now we could simply open the fastmath.dll that does have ASLR turned off, so everything should match the same addresses as we've seen inside of Binary Ninja. And if we wanted to, we could go take a look at the options and preferences, because we should see the default, like, hey, breakpoint settings will allow us to create a breakpoint, or we don't even have to, honestly, at the very start of this thing running. So honestly, we could smartly, safely hit go and go ahead and continue execution. And you'll see that it'll automatically bring us to the start or address of our entry point as we begin execution here. But we need to put a breakpoint, just as we know, right after this big long loop that would XOR that buffer and everything that we want to pull out to get that second stage payload, right? So that is at this address 1800C42E1. We could right click, copy that. And because ASLR is off, I could just hit Control G and that will allow us to jump to or go to a location. And since we're running, we should be able to go find this correct expression as I hit Control V to paste that in. So I'll click OK, and that'll bring us to the same instructions. If I zoom in just a smidge, you could probably see this exactly the same disassembly that we would see inside of Binary Ninja. If I toggle that back to disassembly, yep, there's our call, NOP, and XOR work that we're seeing. So we'll create that breakpoint there, F2, to make sure that that is red. Now, as I do this, I do want to go ahead and hit go once again. Okay, cool. Now our RIP, or our instruction pointer, brings us there. And now everything is in memory the way that we would have wanted after it has decrypted or un-XORed. Hey, took out that hex 33 out of the way. So we could go determine from the data location that we know between the CA758 and the CA750. 750 should be the one that will now point to the start of our buffer. So let me go grab this address. I'll copy and paste. And in the dump, down on the bottom left of the screen, we should be able to go now see all this stuff if I hit Control G again to go to, pasting in that location. X64 tells us that is a correct expression. It'll put us in the right place. So I'll click OK, and this gives us these memory addresses. Now, if I were to actually go follow them, walk through this, I can right-click at the very start. Let me go to follow keyword in dump, and we can put that in dump number 2, since we're already in dump 1 for the tabs here. If I go to this, take a look. You can see the entire MZ header. This program cannot be ran in DOS mode, so we have the portable executable, the whole next stage binary DLL in memory, and we can just extract this out. Now here's the coolest thing. Here's what we can do. We could actually right-click this, really anything as part of this, and try to grab this in actually the memory map. So for the whole memory that we're currently seeing and whatever page part we're actually in right now, we click that, you'll see that it actually puts us into this heap ID 0. That's the one that's highlighted in the about the middle of the screen. Now, if I were to right-click this, we can dump memory to a file and then just give us all the junk that's pertinent to the program execution right now, including the MZ header and the raw binary for our stage 2 payload, and just slap that on the desktop. We can call that whatever stage2.bin or whatever data.bin. We will need to carve out the executable. But because we know MZ, right, because we know how we can anchor and go find that in a hex editor like 010, we've already got basically everything that we need. Let's go open up 010 and let's try to open that. Let me open our data.bin, and now we could simply Control F and like just search for. If I toggle the format here, not in hex, but I actually just want simple ASCII, we know the very start is that MZ, the beginning of our portable executable. Let me hit enter, and there it is. We see exactly, just as we saw previously, this program cannot be run in DOS mode, and now we could carve out this file by simply taking the very byte before it, going all the way to the top, and climbing the mountain here, and then just hitting delete. And then we saved it, right? So we could save this now if we wanted to, or actually apply one of the templates that we know, like an executable template, to tell it, look, you're an executable file. Now, you are a .exe or a .dll. You're a portable executable file. So if we run this, now it smartly adds the colors and headers and everything that we've seen previously, but we could, if we really wanted to, go find the very end. And we don't have to, like this isn't super duper important, but it might be nice if we wanted to, hey, drill down to the very end here. You might be able to see occasionally in the minimap on the right-hand side. I don't know if my face is in the way, so let me move this just a smidge. You can see as I'm scrolling down, there are a couple blocks here like that are blue highlighted or any other important bits. So if I get to maybe the borders that you can see just on the very left and right edges, as I go find these little regions, I'm curious, where is the end? Do we get to one down below? Oh no, we don't. Okay, so this is the threshold that this bottom half does not have a border surrounding it to know that is an important and necessary exe portion. So this 0df0a whatever Don't care. Let's select it all and let's delete it. That is still just leftover memory that we would have saved when we were looking at the binary and we saved it out of x6040 debug. But data.bin now is only our stage 2 dot whatever DLL, right? It's an executable file. We know it's a portable executable file. So let's save a copy. Call this stage 2 dot DLL is probably fine. We could work with that. And now let's start the process all over again and open that up within Binary Ninja. Getting this, usual malware Russian Matryoshka doll one layer after the next. Okay, now back in Binary Ninja, we can go ahead and open up that new stage2.dll that we have prepped on our desktop. Now once I open this, it's going to look pretty similar to what we've seen thus far. If I actually toggle this to sudo C, we should be able to see, just as we have previously, kind of a pretty similar structure to the very start of this code, the same way that the first fastmath.dll did. We know that it's going to do our DLL main dispatch. We know we have our security cookie function here, and we can rename that, walk through these usual steps. But once we get to our DLL main dispatch, you'll know we'll follow through with the if and else statement, where the else statement is what we would realistically take, but jump to the label that brings us back to the if condition, and then this subroutine that actually gets called. So we could click into this, but we start now to do something a little bit different. You can see in this code where we actually start to work with, the process environment block. And some of you might be pretty familiar, that is the PEB. And the PEB is actually some data structure that's inherent to all binaries or portable executables, actual programs that run on Windows, that actually has some really interesting data that could be used and abused by malware, because it can actually keep track of all of the imports or memory object stuff that it might use within the code and context execution of the program. In fact, it actually keeps track of the modules that it might use, like kernel32. Kernel32.dll is one that I mentioned specifically because it will have a method or an exposed function to load library or to load other DLLs, pull in other libraries that code could continue to use. So rather than our malware and the sample being something that could be easily signatured by antivirus, where it has the actual imports for maybe nefarious functions like, connect to a socket or encrypt something or things that could raise an eyebrow, well, it'll actually do some tricks with the process environment block and walk through enough of the data structure that it could reflectively, using its own components, hide and mask a sort of more subtle import or load library for something else that's not then hard-coded or seen in the contents of the binary. It reflectively imports the stuff that it needs with some other tricks. And that is ultimately the PEB walk or PEB crawl. We'll see that in action though. We'll dig into it a little bit more, but hopefully that's at least a crash course in that. Anyway, we know that this data value is going to end up being a process environment block, so we could just rename that to data_PEB or whatever, that's fine. We do see down below, if R2 is equal to 1, a conditional that should just be, again, the DLL startup reason. If that's the case, we will create thread with another subroutine. So create thread will run immediately some new code, and we can call this, whatever, MW malware start function or whatever for our stage 2. Double clicking into this, now we've got a lot more to work with. In fact, this is a much longer function that we'll explore soon, but you might have noticed just at the very, very top, kind of important here, look, they do start to work with the PEB. This RAX1 variable is going to work with data PEB with some hex 18 offset. So I think it's important to note now, we could actually retype this because the PEB, as it's working with it, is going to be a pointer to that type for the process execution block. PEB, that is the, process environment block, forgive me. So let me press Y on the keyboard, and the hotkey in Binary Ninja to retype is Y. We could just change that to a PEB, PEB, with an asterisk right there to denote that is a pointer. Now I'll hit accept, enter on that, and thankfully, this is pretty awesome. Binary Ninja will now just rework and sort of, hey, analyze and give us a lot more of the C-like syntax for the structure components and things that are much more readable as we're kind of examining and reverse engineering this. So take a look. Now we could see how we would pull out parts of the PEB, in fact, the in-memory order module list. And that is, as I was talking about earlier, the data structures that could help the malware author track down the pieces and breadcrumbs that it could use to then reflectively load other modules or other DLLs and get access to code in another new sneaky way. But if I keep scrolling down, we could actually see some of this in that F link, and maybe some of you that have been cruising through Maldev Academy or other resources are very familiar with this process. We could rename this to like, I don't know, MW module list if we really wanted to, but down below, this one is the one that's the most important because it ends up doing some subtraction with hex 10, right? That is going to end up kind of realigning whatever offset as we're working through. We actually want to end up considering that as one of the entries in the loader table data structure entry thing. I'm not familiar with the name off the top of my head, but I believe what we should end up doing is taking that var 3f8 in this case and retyping that to, with a Y on our keyboard, it is just LDR, LDT. No, that should be LDR data table entry and asterisk, again, for it to be a pointer there. I actually don't see it auto-completing those, so I want to be able to add some of those type definitions and structures to Binary Ninja, and I think I can get those online from like the x6040 debug headers that it might offer. Like Google x6040 debug PEB loader data table entry. Here's one result, x6040 debug, source debug, ntdll, ntdll.h. I think this should, if I search for _peb, we do have the peb loader data, and I would like that piece. How about just loader data table entry? Do we have that? Yep, we do. We could grab that just as well. We can actually truncate some parts of this because we don't need all of it. Let me actually get a Sublime Text window open, and I will pull together some cooking show magic. This was from Nordgaren and his incredible work. We had just gotten we kind of cleaned it up and got the Unicode string, just the dependency from the Microsoft documentation, but then the structure for the PEB loader data, the PEB, the other loader data table entry, and all this stuff, we could give that to Binary Ninja so it could more smartly figure this out. If I copy and paste all this back in Binary Ninja over on the left-hand side, kind of like Visual Studio or whatever VS Code, where you've got these icons to get to different things. The type section, if I right-click any part of this, we could actually create types from CSource, and that hotkey. Now, if I were to paste this in, fingers crossed, we've kind of cleaned that up, made it smarter, and given all the definitions for these structures and types. I can just click Create, and fingers crossed. Okay, already a type called ulong. Yeah, that's fine. We can overwrite that. Yes. Okay, seemingly good. Now I could try to retype our var 3f8. And let me do that with that Y hotkey. That should be the loader data table entry and an asterisk with a pointer there. So if I do this, cool. Now we should be able to see the base DLL name being loaded in, and I do want to double click this refresh just to make sure it is going to do all the analysis that it can. Kind of handy though, now we could actually see it's going to end up getting the base DLL name. We could, if we wanted to, hey, define these as parts that we might like to use later on in our code, but it'll loop through this and actually check the length, do some interesting tests down below that are actually going to end up being, I don't know how well you could see this, a too lower implementation, because it actually goes through and ends up taking, if the value that's kind of interpreted as an ASCII number is going to be greater than hex 41 and less than hex 5a. If that's the case, it'll end up converting or adding hex 20 to it, which if you look through the ASCII letters or characters 0 through 255, that actually just means we're going to take what might be an uppercase character and force that to a lowercase character. So it's a too lower implementation. If you wanted to, you could hit the semicolon on this to add a comment in Binary Ninja. You can just say to lower implementation. That's good for our learning, but we will see this over and over and over again because they are now going to do some peb walk, peb crawling implementation to track this down. But they do this in a very interesting way because they actually end up trying to get, as I mentioned, kernel32.dll as one example for a DLL to load functions out of, but they're actually going to do this for other DLLs just as well. And they refer to them all not by, oh, the ASCII representation of like the string kernel32, but by a unique and specific hash or a hash ID that's coming together from their own hashing algorithm that they use throughout this. And we can actually see that in this for loop right here, which maybe we could try to analyze. We do test with an iteration for loop I equals 0, I less than var 448, and we saw that defined up here as actually 3a0. 458 brings us to, another piece that we're all working through. So some length, right, for the string that we're going through. That is literally, as you might be able to say, the length of the string that we're specifying for a name of a DLL like kernel32 or what have you. We could actually rename all this to be like MW string length. That follows down, we can do MW length because that's set to it all just as well. Now when I go see this, we could see that that's what we do over and over and over again. So for each character, we actually try to get information from a data structure. If we double click on this, there's a lot of nonsense there, but that's actually going to be a big list of, in fact, hexadecimal IDs, really, stuff that we'll be able to determine because they do some math here where they add in what would be the ordinal value of a given character, 428 being the index that we end up using here. XORed, you can see the caret symbol here with var 4f8 underscore 2. Shifted to the left 2 bytes, 2 bits, forgive me, also XORed with var 4f8 underscore 2. What is that one? Okay, that is what starts with our hash, or like the hash that we're generating. So let me try to rename that like, hash value, MW prefix. And this is really hard and tough to say out loud, so forgive me. But that is obviously going to be some hexadecimal value. If we know that the data that's represented here is supposed to be a list of these that is being accessed because it's indexing at all of this, we're seeing it plus to add that value moving through the array, we could try to retype this. So with all that said, let's change the type of this data block, as we know that that's really just going to be the hex values like uint32t, right? So Y on the keyboard, let's change that to our uint32 underscore t. And now, fingers crossed, if we hit accept on this, it'll analyze it, change this up, and it'll look like it's actually indexing. You see these square braces kind of just denoting the very beginning and end of this. So now we've lost the shift to whatever left 2 bits, but now we're still doing this with a shift to the right 8 bits. And there is actually one more tidbit we can add to this to help make this even easier for us. And this probably shows a good learning lesson for when you should kind of always be back and forth between, sure, the pseudo C that we like to read because it's easy, and maybe just the pure disassembly. Because if we were to actually kind of split the window here, let me try to split pane horizontally so we can get something on the right and something on the left. I know this gets a little bit hard to read with my face in the way, but over on the right one, let me say that I'm just going to click in on that very exact line where we are indexing from that data buffer to determine the hash value in the loop. But if I move this over to the other side, and if I were to say, okay, show me the disassembly here, you can see I'm at that instruction, but if I kind of take a look just before all this, it is going to end up indexing and working with all this stuff from EAX. But EAX is what ends up being worked with just previously, actually coming from ECX. And ECX is ANDed with hex FF, which means it's going to only be within that bounds of hex FF or 256, right? So if that's going to be the component that's really used to index out of the data buffer, it's probably pretty likely that our data buffer, going all the way back down here, is really at a length of 256 entries. So let me retype that one more time. We know it's uint32_t as we've added, but now let's actually supply the length 256. So when I accept and hit enter on this, now we've got that analyzed, a little bit smarter to index this, and if I actually double click on this, it's a heck of a lot easier to read, and this is much more clearly all these ID values that will match a hash for what we could be looking for in the hash algorithm to determine a DLL name that we could import, as our malware will do what it does, and then later maybe a function name or method that we want to call out of that DLL. So this is awesome. This is data that we could use, and we could actually recreate the hashing algorithm and then determine what is it going to do and what is it going to load all throughout the rest of this code. So totally, we want to go copy all this and then start to work with it. So all the way from the top and the bottom, what we could do is copy. In fact, copy as CArray is probably best. 32-bit elements, little endian is what we're going to be looking for. Now I can get back into Sublime Text and let me open up a new script where we'll actually start to write some Python code. Let me save this. Let's just make it a .py file where we could build out our hash checker.py. Good. And we could change this to an actual list in Python. So let's remove some of the C-like syntax and make that just a hash table equals. And now we basically want to build out the same capability that they did with the hash function, where if they were given a string, remember an input string for a DLL name that they were trying to find, like just for an example, let's say DLL name can equal kernel32.dll, and let's define get hash ID given a name, right? String name, whatever. Of course, this is where you saw that string name dot lower. Remember, they had that toLower implementation. Not super necessary for us as we're starting to play with this, but they looped through every character in that string name. And they took the ASCII value, which was the ordinal in Python, the ORD function we could call. And if we look back at what this was doing compared to the C syntax, going back down to the for loop for our hashing implementation, you can see that they grab that value, they XOR it with a hash value, and that's the current hash value that they started with hex FFFFF whatever, but then they end up working with it throughout because they're updating this, and then they change it and reset it at the very end. So that's all stuff we should know. Let's build that out. Back in our Python code, let's say hash value equals hex FFFF for Fs. And then inside of the loop for the character, we grab its ASCII value, we XOR that with the hash value, and remember this is going to end up being an index from our hash table, right? They do index that just as we've seen here, and that is going to be then XOR'd with the hash value bit shifted to the right 8. So do that with the hash value, and let me move this up to make sure you can see it. Hash value bit shifted by 8. And that should be the new hash value. Everything that returns is going to be that. Back in Binary Ninja, we see we just increment the character. We don't need to do that in Python because that's already been done for us. But in the very end, we do the hash value XOR'd with hex FFF all over again. So I think we can add that at the very end, right? Let's return our hash value XOR'd with 1234, 1234. So can I now try to get the hash ID for our DLL name, kernel32.dll. And if I print this, oh, broke everything. I have an error. List index out of range. Oh, that's the hash table tidbit here. Binge is not showing me that because it probably doesn't need to, but that is still ANDed with the hex FF, right? That's to only say, look, we're only going to get something within the range of 256. So let me update that to everything in this index inside of the square braces. I want to make sure that that has another AND hex FF, right? Let's try to print this, and let me build view this in the current page. So you should still be able to see this as a value. What is that in hex? Can I run that? 6AE69F02. That looks a little bit familiar because that is exactly kernel32.dll that they try to load first. Cool. Okay. So we have just recreated that hashing implementation, and now we could track down not only the DLLs that they load, but now all of the functions that they will reflectively walk through with this pebcrawl. And we could see this kind of just honestly ignoring or abstracting a lot of the stuff that they do later, because we'll see this process again and again, now with a new hex value. But this is where we could do something really kind of interesting, because if we were to say, okay, kernel32.dll, I know even just, I pulled that example out of thin air because that's just what we're used to with load library and all these examples here. If it's trying to grab some other functions, it would be worth knowing what the names, literally the string representation of all the other potential DLLs are, and then the functions that could be called from that. Now this is where some of our sweet friends over at Malware can come in handy, because they have helped put together an awesome resource for exactly this. So let me say big shout out to Malware. Seriously, genuinely, this is pretty cool, and I hope it's a good resource for others as we are trying to learn and walk through this process. But look, these are all genuinely, literally strings for DLLs that could be loaded, but then all the methods or functions that could follow. So this could get kind of crude, a little bit scrappy, but if I were to look for kernel32, if I could type correctly, there it is, and that could very well be the hash that we might end up working with, and all of the functions that could come through and follow that. So if we were to use this JSON file, common_dlls.json, we could take our hash checker capability and give it a little bit more instrumentation to now look up, based off any DLL name that we want to look for, what is that hash? Let's minimize our getHashID function here. DLL name isn't super duper important, but if I were to open, so let me open that common_dlls.json, just read as bytes, doesn't matter. We can do that as file pointer filp. Honestly, we don't need the mode here because we just want the file pointer, and if we were to import JSON, then Jason, our good buddy, could totally help us load that filp file pointer. That will determine that as the DLLs that we actually will end up reading through, and given that, we could look through every single DLL, like DLL name in the DLLs. And note in that JSON file, they don't actually have the .dll suffix, but we would want that because that's what we built out for our implementation of this getHashID function. So DLL could equal DLL name plus .dll. Stupid and dumb, but that works. And we could generate the hash, like we could just simply say the hash of that DLL is getHashID given that DLL, and check if the hash is something that we want, like maybe we're looking for a target, like target hash ID is probably a fine name, and that was something that we started with going back to Binja, right? 6 this, we could copy that value. Knowing that that is kernel32, that should be all that we need. Let's add that variable there. If that's the case, then we can print the DLL and like a found appropriate DLL, adding that. And then we can loop through all of the other functions in that because we know, okay, they're probably then going to, after they've loaded that specific DLL, now call a specific function within it. We can say for each function in the DLL's JSON data, given the DLL name that we're looking at, now get the hash ID of each of those, because it's all coming from the exact same lookup table. Get the hash ID of each function, So we can say the function hash will equal that, and then let's actually print out each function name and the hex value, just as we've seen above, of the hash that we've calculated. So with that, we could totally build out, we could do like an else statement here just as well if we can't find that. Could not find DLL module mapping to ID. Now we have this given capability to get not only a target hash for a specific DLL that we're looking for, kernel32.dll in this case, but then we'll see what all the other functions will correspond to, and we can just kind of map back and forth. Oh, did I break something? Yeah, I broke something clearly. Oh, the else statement doesn't need to happen because we could do that after our for loop, right? You can do a for else just in case we never find anything. We just won't care about that line, but now we do clearly see all of the functions that will be called given a hash ID, knowing that we did see that in kernel32.dll. So here is where we can put this to the test. Let me copy all of this data, put this in a new buffer for us, and let's say that in Binja, we know kernel32 corresponds to this 6AE value, that hash ID that we've uncovered. Scrolling down, we'll see it now trying to work through the same for loop implementation and trying to determine what would be 906A whatever. So if we copy that hex address, now go determine, not an address, but an ID value for us, right? Our hash, that corresponds to create thread. That is the function that we know it's reflectively pulling in and grabbing thanks to that kind of process here and the peb walk that they do. Very, very cool, because now we know that we've determined this, actually been able to pull it down, grab that value, and ultimately inside of this condition, we know, let me rename this to our MW create thread call. We can hit accept on that and then see it's built that out. And now we're going to do this over and over and over again to go grab other functions for it to use. We can see another kernel32 instance that we end up using. Scrolling down later, we go determine. It's going to grab this hex value, so we can copy that, get back to Sublime Text, look for that. It actually gets sleep from kernel32. Okay, MW, let's rename N to change that, our MW sleep. And we will go through this process over and over and over again. But look, at the very end of this, we are getting to another create thread where we see it move to another new subroutine. So it's going to invoke something else. But if we jump over there, we do more peb crawling, peb walk, and we see this over and over and over again. So I'm going to be honest, I'm going to walk through this process, kind of speed it up, and then I'll let you know how far we can go, but now we see the alloc console. Rename this just as well. You get the idea, so let me cruise through this. And I know it's a manual method. We could absolutely, without a doubt, do this in an automated way with Binary Ninja or some of our other tricks, but I do want to show you this process and tell you, really, that's all I'm doing right now. We've got this ironed out, where I'm just going to end up looking for changes to when we get to new capabilities for imports, and then if we see a different hex value rather than our 609 whatever for kernel32, we just swap that out in our Python script, get a new lookup table for us, and then we keep cruising. Ooh, actually, we do get to a new interesting part where we start to see some pieces of data that look to be encoded, or at least in their hexadecimal representation. You can see the \x prefix over and over and over again. But these are pretty clearly, as we can see within Binja, Binary Ninja showing us, hey, we have this variable stage var 1a00, but another that's just below it, var underscore 22e0. Seeing these two together, we tie them and end up getting these XORed super easily. So what we could do is, again, super small, simple, copy this value. Let me copy as I believe, hex dump. Oh no, raw hex, forgive me. Raw hex will just give us the 6C9A E5, the values without the \x in the mix. So let me hop over back to Firefox, where we were working in CyberChef just previously. Because now I could paste in this hex value. And we know that the key, or the operation that they do the XOR with, is just the other value. So I could right click this. Let me make sure to copy the correct value, copy as the raw hex once again, bring that and use that as the key. And now you can see in the output something a little bit more peculiar, real data here. Now this specific string has a very unique and special use case that we might be able to talk about later. It will determine how long this video is. I think this is already a ginormously long and lengthy video, so we'll see. But we'll see this pattern again over and over and over again as just data that we could XOR out pretty simply. I do want to keep cruising to see what they do next for their PEBWalk. We can see a couple other cases that they use the process environment block to see other functions that they will import and work with. Oh, looks like there is a new ID. So again, we can just use this and go put that in our Python script to determine a new target ID and see if that will give us a new DLL that it loads. Yes, looks like there is one. So let me go bring that into another tab, and we're actually looking at NTDLL and all the functions that could be included in that. Follow along the exact same process. Oh, they do some interesting stuff with NT-allocate virtual memory though. You can see this then actually being used just below, where they do create some memory that they can work with and actually write some machine code in it. And I won't drag us down the rabbit hole, but this is actually really clever, and we'll see it used later on, or at least we know that it will be used later on when we get to the rest of the implant here. But look, they use NT-allocate virtual memory to stage some data where they actually write machine code that ends up being a hook, like a function hook to trampoline to new code execution later on that will be the actual detonator for stage 2 that actually writes this address to end up putting the capability that will be used in the real program that we'll see later down the line. But just note, this segment is actually a little bit spooky. They do write a genuine function hook here to run the real payload super duper soon. The strange string that we saw earlier from that XOR operation, remember our new from UTF-8 string, that is used by the real program that we see affected later on. And that is genuinely a hook for that function, all with some cool, clever, unique NT-allocate virtual memory. And later on, when we see some other PEB work, they will protect that memory and do other shenanigans with it. Here's that NTDLL one, and we could see another copy or a hex ID that we could use. Show you that in Python. We'll go now find that NT protect virtual memory. Scroll down and I'll continue that process again. Oh, we do get to the very end here though, and we start to do more NT-allocate virtual memory shenanigans, so making a little bit more unique, special stuff. But then we invoke something with some more data. How does this happen here? Basically setting some data buffer that looks empty to start to a variable var2900, and then that is going to end up being the result that's returned. But how did that happen? It's all seemingly zeros to start. So what is this var2900, where does this come from? Let me trace that back, scrolling way up. We could see it in the cross references in the bottom left, but that might just jitter us out of where we were. So I'd like to kind of see, is it in this function at all, even to start with? Let me just do some manual scrolling. And yeah, it looks like it is where, oh, interesting. This is used with the syscall opportunities and the NT-allocate virtual memory, the stuff that it writes. Oh, that's building a legitimate address though. But we know that this is used at the very end of this function, and they don't do a whole lot else with it. It is seemingly executed though, or brought to life. That is going to be a static address written to this buffer though, that data 1800-1A140. So if we wanted to be a little bit lazy but still more accurate in this, we could hook up our stage 2 DLL to a debugger and see what value is going to be written here when we actually execute this. Do some more dynamic analysis. That does mean, though, that we'll need to go through that 010 editor process again to disable ASLR and kind of work through that again. We can do that super quick, though. Let me go ahead and open up our stage2.dll. We'll work through the very same process with the NT header, optional header, bringing that down to the DLL characteristics, and the dynamic base, we'll set that to 0. Save that file. Back in x64 debug, we could just go open up our stage2.dll. We know our first breakpoint should be fine, so we can run this. But getting back to Binary Ninja, we know that this line is when that data actually ends up being modified and is set. So we could get this address. Let's copy that address. And then back in x64 debug, let's try to Control-G to go to that address. There we are. Now we can set a breakpoint there. Should be F2. Now let's continue up until that position, and we should now be able to see the data at this address is going to be filled with something. So let me double click in here, grab this address, and then we can see that in the dump, way down the bottom left of Hex64 debug. Control-G once again, we'll hit enter on this. Now this is all zeros at the moment, but this line is the one that does actually set the value there. So the address will be populated, and if I step over, I believe is F8, there we go. We can see a new place set. And actually, a little bit interesting, just as we were talking about, that strange string that we saw earlier actually ends up being used as an inline hook. But we'll talk about that more. Let me get to this address. I want to step one more time to see if this changes that. It does not, so I think we're okay. Let's just grab this address. Let me follow keyword in dump. We can go to dump 2. Now you might be able to see, but this little second line here is actually an address. It's probably easier to kind of identify that one because it does start with that 018000, like the base DLL address. So we can actually change this to view as addresses. And now take a look. There is that we were just looking at, and it actually tells us, hey, we could expand out the little comment here. There is a location that is part of this binary. So if I double click on this, copy this value, the expression there, we could actually go to this. If I Control-G in x64 debug, that is still a correct expression, to a new location, and we could do this in Binary Ninja and go see the next location that this would go to. So back in Binary Ninja, let me hit G, and I'll paste in that address, and here we are at this thing that would be called and hooked by some other V8 function that we'll see later on in how it's actually brought to life. I think it is really worthwhile, though, that this does have some pretty interesting stuff. In fact, you'll actually be able to pretty quickly see more XOR strings that we could now uncover and get even more secrets out of this binary. Again, this isn't all too hard. We know this process already. Let me right-click as raw hex and then go put this in CyberChef to simply XOR and decode that. We'll paste this in at the very top for the input, and passphrase seemingly here. Did they use the very same string as the key? Let me copy that once again. I'm pretty sure that should end in D3F5. No, that's different, but it gets, okay, probably the same length. Yeah, the very start of it still works just fine. Can I URL decode that? That is just going to get what would be like JSON data maybe, because it's a colon following a string value. Is that going to be used to cut up something later on? That's a good thing to note, but we can get back to the rest of this. And again, I think we're probably going to run into pretty similar PEB or the process environment block walking procedure. In fact, as I scroll down through this, I think we're going to end up seeing a lot of the, data PEB in memory order module list, while loop, and kind of cruising through this. So we can use our Python scripting once again with the hex ID or the hash that we've determined, and then go see what functions this calls. I'll try to make a list, but I believe there are a lot of these, so this might be a lot of back and forth. Double checking this with our list and our Python script, looks like this will be another NT allocate virtual memory, and they use this just down below. We can see the call there with that usual memory permission right value. And look, down below, hey, they have even more XOR strings that we can carve out. Let's keep cruising through this and see what else we could get. CyberChef is a quick and easy process. Whoa, what is that? We grab the XOR key so we know we have that right thing. I'll include that. Pricing a Exodus IO ticker. What is this? That looks real. Let me go to that URL. Pricing a Exodus ticker. Assets.from must be an array. What is this? Route get not found. What is pricing.a Exodus? A Exodus.io. Oh no. Of course, a Bitcoin and crypto wallet, Exodus. What is this going to end up doing? Is this going to end up trying to steal cryptocurrency? Do some other stuff? Oh, we saw that passphrase string. Maybe that will be used, and this is just going to do Exodus stuff. Let's keep going. I think we are getting more bits and pieces that we can, again, even just kind of, hey, put the puzzle pieces together. Knowing the Peb walk, the crawl that we have, we can see all the values that it might try to grab. Here is another. Swap that hash in. Create thread. They do that again with a new subroutine. Is that the very end here? Oh no, they keep doing more, but what do they invoke with this? This isn't a whole nother subroutine. I gotta go to that. More Peblock. That is a different hash value, I think that I've seen before. Let's try to see what this one will do. This is ucrtbase.dll. What function do they call from there? They call getEnv. Okay, load up the environment. Looks like they immediately continue another Peblock with a different hex value. Let's grab that one. We can use this, and that actually brings us to... Ooh! WS232.dll. That could very well be used for like socket connections and communication, right? This could be either, I mean, jumping to conclusions. Oh, some command and control. It's not. Let me say that. But they could be exfiltrating some data with sockets and stuff that they connect back to. So this could be pretty juicy. Let's keep cruising. Let's grab another hash value that they use here. That is going to be WSA startup. Yep. Do they call this soon? I mean, obviously they're just getting all the functions that they need. So we'll see this again and again. Let's keep grabbing all the capability. Next one is socket. Continuing, let's get another. iNet adder. Continuing, what is this one? HTONS. Next, connect. Yeah, okay, so it's definitely gonna make a connection, without a doubt. Then we'll continue with this one. Send to. Okay, exfiltrating. And then other functions here. Close socket. That's it. More Peb crawling. Still, there's so much here. WSA cleanup. Oh, duh. Get host by name. We gotta automate this next time, but that was kind of a fun, at least walking through and showing you the whole process. But we do have more XOR strings. So what do we got here? CyberChef, all reliable. Let's paste that one in. Whoa. Let me grab the other tidbit. Let me copy as raw hex. Grab that. Whoa! Look at this. These are totally URLs and absolutely the location that could be like command and control C2, or at least, hey, exfil. Like that is threat actor infrastructure without a doubt. Let me open that up just in Sublime Text so we could like jot those down. Oh, they're all null bytes. So sweet. They totally are supposed to look like Microsoft Defender and like look like Windows, like official things. MS Analytics, MS CDN. Are these still live? Are these meant to be just straight websites? No, probably not. Analytics. What about this one? No. All right, can we ping those? We could try to like look them up, do a whois, do whatever enumeration we might like. Just simple ping. 4.9.149.215. That's the IP address. How about this one? Let's ping that. The exact same IP address. How about CDN view DNS? Ping that. Oh, do not know that one. Okay. Well, presumably the others, I would assume, maybe if that were a domain that was still like in circulation or whatever, it would still point back to exactly this. We could track that down in like Census or Shodan. Let me enter that IP address, 45.9.149.215. We can go ahead and search for that. And Ubuntu Linux server with SSH open, presumably, over in the Netherlands. And granted, that's this current time. If we were to try and take a look at the history, does it have any old data? Not a ton. But with that, we do very likely have the 3 domains that it would try to connect to and that IP address, the 459.149.215, very, very likely being, okay, what they'll all funnel back to, that actual server. Honestly, at this point, I feel like we can kind of take the high road because, look, we're getting juicy information from these hex strings that stick out like a sore thumb. So I don't know if we need to go through each and every little thing to, reverse engineer or try to make sense of. I think we're already in a good spot. Let's use CyberChef again to enter this with, what is that? Let me copy this, entering that XOR key. What is this? Is that this? If we're thinking crypto, right? If we're thinking Bitcoin, crypto wallet crap, is this the wallet? Is this like the wallet ID that it will very well maybe send money to? Totally in speculation right now, but can I look that up? Is there like a blockchain explorer? Because this is Exodus, right? And at least we're assuming that that's the other string indicator that we saw. XD, probably pretty likely XDW sounds for Exodus wallet. I'm going to go on a limb and say that's got to be the wallet address that they are going to send money to from probably stolen funds on all the affected, impacted, infected, and compromised hosts where this mod and this malware actually gets ran on from an Exodus wallet. Is there like a blockchain explorer for Exodus wallet? Because it'd be super cool to see how much they've either gotten or their documentation. Can I find transaction ID? I've never heard of this Exodus thing. I don't know crypto. I don't do crypto. So normally I just how can I find a thing on Block Explorer? But I don't think there is one for Exodus. I would be super curious. I mean, there's got to be one, right? That's the whole kind of point of the blockchain, right? It's supposed to all be public. If anyone knows, or could we track down or get any info from that unique string from the wallet, what looks like, I would be super duper interested in whatever we can track down. Keeping it going, there's still even more. Another one is a wallet again, but then they have more PebWalk. So we will eventually get to actually calling these functions, right? I feel like there's no reason to do this over and over and over again for even functions that they've already uncovered already, but that, I guess, is just how it's written. Dumb, crappy malware code. What's this? fopen. Oh, are we starting to work with a file at this point? Another value. We use fseek. Okay, we gotta be doing some file operations then. That prefix f is deferred to opening local files. So maybe we're going to end up doing something to read what could be the passphrase for the secrets for that Exodus wallet, right? Or anything else. Let's kind of keep cruising. We now will ftell, okay. Grab another. fread, yep. And fclose, yep. Okay, now down below, we have sort of the same setup where we saw those hexadecimal values all together again that I sort of skipped over or ignored just a little bit ago. But if we actually look at these variables, the values, the things kind of being set, it looks like they do end up really being used in another XOR operation. They do this with the ZMM0, which is kind of repeatedly set to different values that end up being pulled from other values above. But we can assume, okay, it's another XOR, just like we saw with the string values of all the \x or hexadecimal values. These are probably just not long enough that Binary Ninja would end up automatically displaying or kind of converting them and showing them as strings. So what we could do, and I should have done this earlier, but hey, maybe a little trick that we could do is take this value. Like if I copy just the hex value, if I open up a new window, like Control-N on my keyboard to literally open up a new tab, we could right-click and paste this in, but if we paste it as just the value itself, it's not going to really display all that well because it's going to include the hex 0x prefix. I want it literally to be interpreted as hex. So what I can do is right-click and paste from an integer list, and then I don't know how well you can see it. My face might just be in the way, but we will actually paste as a 64-bit element little endian. And I'll go ahead and do this. So that's a little bit easier to see. Now we can paste that, and we'll do the very same for what we know is just kind of a continuation of this, and it looks like they use the very same ending even after for both ends of the XOR, but it's still good to kind of copy. We can right-click, do the very same, and now we'll paste once again in that integer list 64-bit little endian. Now I could copy or Control A to select all of them, and not strictly copy, but if we right click to transform, we do have one operation here to XOR. And we can do this all within Binary Ninja, which we probably should have been doing all along. Like, we could do it as we have done through CyberChef. That's just what I reached for in the moment. But Binary Ninja can do this just as easily. We can XOR, and then we can provide the key or whatever we want here, and we could paste in all the other values in the exact same way. So this value up here, let me copy this. I'll copy just that value, Control C, and we can right click to paste. But actually, you will need to go through the menu here where we actually specify this, because Control V won't get the right format. We can do the very same with the other. Paste from, integer list, 64-bit elements, little endian. Now, if I hop back over here, the moment that I click apply, you should be able to see this value, all in ASCII here, username. And the reason why I wanted to focus in on that one and make sure we include it, because, hey, at the end of the day, you'll see the end of this operation after the XOR, ultimately this value. And note, they do use this in the get environment call that we saw pulled down from the PEB walk, the process environment block walk. So let's rename this to be like username. We can accept that value, and then it's set, and we'll change up all of our display here. And it's interesting, they do allocate some memory to be able to work with this, and then they do this later on. They have another sort of setup and structure with more XOR later down below, and we can do this exact same technique where I copy it in and out of just a new window for us to work with it in. This is just the very same operation that we're really doing in CyberChef, but hey, saving us from going into CyberChef, and now we can do it with those hex values rather than the string that we saw. So I'll walk through this again, and I'll speed through it so you don't have to listen to it all over again. Looks like that is user profile, a worthwhile string that it's going to get out of the environment. Once again, we can see that value being used just down below after it is set from its XOR operation. This ZMM0 kind of takes that value and ends up being what is being set for this, which we can rename to user profile. Now, this is kind of interesting because they do this and then they have some more strings down below. And it just, for, I don't know, the convenience, we can copy as raw hex again and go do this in CyberChef, nice and easy, because we know we have that process ironed out for string values. If I hop over here, we can replace the input, and I paste in this, and oh, what is that? You see that down below? That's another app data roaming Exodus. There's that crypto coin crap again. Exodus wallet. seed.seco, bunch of null bytes at the very end, but the %s I'm going to assume is going to end up replacing and putting in our user profile environment variable, which is why we saw us get environment that, and that's going to be really a sweet string to probably get the wallet information, like the seed for the crypto wallet. It's worth us jotting that down, because the victim wallet will have all the funds or the seed information taken and then maybe transferred to this other account later on, presumably. I know they use this as a key, and I'm not sure what this other one is being used for, and they do have a dangling leftover XOR value. Like, copying this back inside of CyberChef does not seem to get anything, so maybe that, I don't know, we could spend more time on that, but I am super duper interested in that seco string. Presumably, if this does end up being the value after it, oh yeah, take a look. Look, they use this swscanf string based off of what would be seed file path. It's probably a fine name, where what it retrieved for the user profile, MW user profile value, that's going to end up being put into this new value after it does the format string conversion, right? So let's rename this to MW full seed file, accept. And now we have more string modifications down below, but that ends up being, let's go through this quick XOR process once again for the hex values that we're working with. That is just the string RB and the null bytes all the way at the end. What is that used for? Did you have that value set? Oh, just down below. Oh, for the mode of fopen. Okay, cool. So we're getting to some of the functions that we saw earlier, and obviously MWRB string there. It opens that seed file in read mode and pulling out bytes binary with the B prefix there. Gets the length, I'm going to assume, with the tell operation. So let's just say MW file length. allocates enough space for it to be able to probably read in data from it, hence the MWF read there, closes it, tries to get data, and down below, it looks like it is going to end up like iterating through the contents up to the file length, if that is in fact the file length, right? And then it does something, a little bit more. I don't know if that's to like cryptographically determine some value or something inside, or maybe some representation or decoding, whatever algorithm might be inside the contents of that seed file. But eventually, we move out of the process with that file, and then we start to do, the WSA startup, where we could enter a new callback, get host by name, and try to connect to this, right? Do we see the other functions? Yeah. MW connect, MW send to, close socket. So it's totally going to make a connection, and it's wild here because this has to be an iterator for all of the data values that we would have seen based off of these 3 command and control servers, or exfil locations, right? Hence the, minimize this, hence the less than 3. So it iterates through, and we can call this like MWC2 iterator, which obviously indexes at that data. And then it will use that as the host name. And this HTONS is likely going to be used for the port value. So I don't know if this will match what we saw previously when we tried to look things up on Census or Shodan, but maybe some values could be wrong. Let's try to just see that in decimal representation. So let me just do this in Python super quick. We can paste in, that 063DD. So port number likely 25565. And then we know that it'll make a connection and then send some data based off of, the socket object. This S45 and var, that's the connection, maybe object there. Something that it's kind of handling back and forth. What is S_45? Is that exactly what we've uncovered from our file that we just read above? So I'm going to assume, right, we can make enough of an educated guess here to say that it is exfiltrating the seed data from this Exodus wallet. And then we get down to the very end of this, we do a little bit more string stuff, and that gets a value software MSCDN2, presumably, which is going to end up being the XOR operation for LP sub key. Rename that variable so that's a little bit more clear. And it opens the registry, probably one of the constants or values for like HKey current user, and then sets software MSCDN2, writes that with the handle, closes it, and then exits out. And that's it. There is nothing else to this code. That is it. It will open and read the Exodus wallet, grab the seed file contents, and then push that out to those 3 domains that we've been tracking all along in the IP address. Also notes the wallet information, but also creates a registry key that doesn't seem to do anything else. But that is the end of stage 2. There is no more code. There is no place else for this to go. And that is it. So if you ask me, a little weak sauce, kind of a stupid implant, I guess, for the capability of, 350,000 or whatever affected players, this mod that ends up just stealing from a super obscure crypto wallet. And granted, this is stage 2. We were going way back to our fast math DLL. If this were to follow through, what would happen next? Like, I know we fell down the rabbit hole for the breakpoint that we had set way at the start to get stage 2 out of that data section after it is unXORed with that hex 33. But if we were to continue onward, we would fire up another subroutine that actually ends up putting together a runtime log.txt. I'm going to assume that's a file, right? And hey, there's other subroutines and stuff that it tries to call. Go to label operations. We can just kind of scroll through this to get a quick gist. But way down at the very end of this stuff, we do see it create a file, which we could see dynamically with the debugger or even like procmon, and then writes the contents and moves a file between what it was and now to something new. So we could probably see that and try to get a better understanding of what this will do to remain an implant. Oh, it deletes the file just as well. Oh, the old one, I'm going to assume. But that is the end of stage 1. So let's try and do this dynamically. I'm going to be a crypto bro for a couple moments, and then I guess just get the Exodus wallet and try to see how this would work on the desktop. Will it be able, if I add some breakpoints or even just monitor it with like procmon and sysinternals, would it create a file or leave behind some other artifacts? Or let me see what it would do for real. I won't have any funds in here, obviously, but I just want to be able to see if it would steal that file. So I'll install Exodus. Okay, so now we have Exodus as the wallet. And is that path that we saw for like the wallet location, is that real? That's probably the first thing we could track down. Is that a real genuine seed path and location? We had that in our Sublime Text notes, so that would put us in app data. Let me just go to %app data. That will put me in local. Oh no, that will put me in roaming by default. Okay, so then Exodus, and then Exodus wallet, seed.seco. Gotcha. Seed.seco is a binary file though, is it? I mean, that's probably why we saw the mode being RB for that argument to fread. So let me try to open this, and of course it's going to be nonsense. So in stage 1, way back in the very first fastmath.dll, let's try to run this dynamically now, since it should trigger or invoke and detonate because we have Exodus wallet installed and that file would exist for it to take. Let's see if we could set a breakpoint and run this dynamically for the create file call along with the move file call, and let's see some of the other locations or paths that it ends up interacting with. Let's do this with x64 debug again. Let me close out of stage 2 and let me open stage 1. Let me start this to hit the very first breakpoint so everything is mapped. Let me control G to actually go and set a breakpoint on what would be the create file call. So we'll hit F2 there. And then we'll do the very, very same for our move file. We can hit F2 on that. So let me cross my fingers. If I hit go here, we can get ourselves to the create file call. And then let's double check what is actually in the address space here. Oh, look at this. Look. I'm in dump 1, and of course you see the MZ header, likely buffer that's kind of accessible. But over on the right side, this is the stack, I believe. Data in memory at the very least, and we do have our app data local Exodus app 24.41.6. So it must be the local path for Exodus, the Exodus wallet. Let's try to navigate to that. I was in app data roaming just a moment ago, but let's go to local, and there is Exodus, and then app 2441.6. So presumably it will create the file with the file name runtimelog.txt the moment that I step over this. So let me put this to the side, and then I move our debugger over to the other side. Can I just press F8 on my keyboard and then see if this side will update? I don't see it here, but this is running from our desktop. Is it created there? Yep, okay. There's runtimelog.txt. We could open that in Sublime Text. Not yet written, right? Because we would need to step to the write call, which we could see down below. We could F8 to get over to there. Go. Let me actually close it out in Sublime Text so it won't have the handle taken. Go. Write file. Close handle is probably a good thing to do just as well, but now going back to runtime.log, of course, it is the MZ header. You can see that in hex. It is the binary file. It's leaving stage 2 momentarily as a .txt file, but what does it do next? Oh, do you see that? Way over on, again, in our stack or some data that's here, it's going to end up putting this to the app location for Exodus, profapi.dll. So profapi.dll, and obviously once we move down to our move file call, it will put it exactly there. You can see it all the values here, RDX, etc. So now if I get back to our app, we should be able to see this. I'll hit F8 again for it to create that file. Was not there previously, but let me step over this call, and then you'll be able to see there. It was added down below for profapi.dll. But it put it specifically in this location as a means of persistence, which is kind of neat and kind of cool, because if this file didn't exist, it is a DLL. It is literally a library that will end up loading as the regular startup of Exodus. And we can see this with Procmon. This is also DLL sideloading. Or to be more accurate, like a DLL path hijacking or DLL search order taken advantage of, because we'll put our own profapi.dll in this location rather than one that it would try to search for normally. We just put a custom rogue one there. Let me delete this file. Actually, let's stop our debugger and let me show you that, because if I were to rename this to like the malware.dll, let me fire up sysinternals so that we could actually see with Procmon. Procmon 64, yep, that's fine, we can run. I want to look for specifically where the process name is exodus.exe. Let me add that, I'll click apply, and then we can make sure that is listening. And I will now go start the real exodus.exe, and you'll see all the activity here. But if I were to stop listening, let me control F for specifically that file name, profapi.dll. Of course, it's going to load this. You can see this down below. It tries to get a handle, but it is name not found because it does not exist by default. But we will end up creating it when that malware is invoked. And it'll automatically load it and automatically execute it every single time the exodus.exe wallet and cryptocurrency app is opened. So clever tricks, kind of cool little tradecraft, if I may say. Couple neat things that it does to get execution and steal this cryptocurrency. But I am giggling that that's it. Now, if I were to go way, way back to the very start, remember we were looking in Discord, and I was trying to give a huge kudos to the community, the whole, hey, communal contributions and everyone's hard work and efforts to dig into this. I was very, very late to the story, but Loch Ness, Illuminati Fish, and a whole lot of others, part of the JH Discord, really got to dig into this, and I felt so cool to be the place where all the answers were coming from amongst this situation. Like, I know there was communication between Paradox and their forums and others, and we'll explore that and talk about it in just a little bit, but I did want to give the big shout out to Loch Ness and his write-up here that he published that covers everything that we have just uncovered by doing the reverse engineering process. But hey, that is the write-up, that is the TLDR that I didn't want to show at the very, very start of the video, because I did want us to walk through that whole experience and do the full analysis, but I do got to give the props, and I absolutely wanted to offer this as a sweet thing to dig into it. Big shout out to them, and I love the name they called it. They wanted this to be Exo Tickler. Good FAQ there and a little bit more tactical information for the players. Thank you for being really genuinely great stewards of the community. Now that we're all done with the technobabble and reverse engineering, let's talk about the aftermath of this. And I do mean genuinely, hey, let's just talk about it. I know this is speculative conversation here. But the mod developer had their account compromised, and that is how the bad actor was able to update the actual mod and push that out to all the other players. The mod was malware because of the affected developer, and there is a lot of conversation about this over on Discord. In the early days, when there was a lot of uncertainty, someone did find, hey, this actually looks like the same thing that came through from a Grand Theft Auto mod some time ago. This is actually a little bit interesting because that Grand Theft Auto mod does have the very same DLL. It has a different file name, but the exact same hash, meaning that it is the exact same file. Even for some extracurricular, we could go back and go take a look at that Grand Theft Auto mod, validate, make sure, yep, genuinely, the hashes are all the same. But my goodness, there are so many things that say download on this website. It's no wonder that people just, hey, get malware. Is that the right one? Did I just click an ad? Okay, no, I've got a link. Good. Yep, it does contain a virus or malware. Thank you. Good work. The Discord said that the file was umpdc.dll. Yep, okay, let's grab that one. I can paste this on the desktop, and I do have the original fastmath.dll now, not the modified one where we had just changed the ASLR bit. But if we were to compare these two, let me open up a terminal. I can move into the desktop, and then I can get file hash on the fastmath.dll, as we're expecting the 8C, 6C, whatever. Now, if I were to do the very same with our umpdc.dll, it starts with 8C, 6C, 3F. It is, in fact, the very same hash. In fact, there's actually a little bit of an Easter egg with this. If you remember back in Binary Ninja, while we were doing, kind of closer to the end, some of the XOR tricks with these hex values that weren't as long as they were when we've seen previously in an entire hex string, and we didn't use up until kind of close to the end that trick of XORing them within Binary Ninja. I remember I had skipped over a couple of those just because we weren't quite sure how to approach them in the moment, but look, now that we're a little bit smarter, if we were to go back to the ones that I ignored and skipped over, this was after some of the PEB walk, but before we got to some of the functions that actually did the exfiltration technique, we'll find something a little bit interesting. So I'm scrolling way back up to the top here, and forgive me, I think you'll see some of our variable names that might still look a little bit odd. Going back down to it, yeah, we have that MW software MSCDN2, just the reg key that we saw at the very end here. But a couple of these hex values that we could still XOR, now using that trick in Binary Ninja that we didn't use until previously close to the end. It is using the same hex at the end of both of the values here, so we really only need to care about the first ones. But if I were to copy this, go do the same trick we've been doing previously, where we paste this and then XOR them, the moment that I hit apply here, you'll be able to see an interesting string. GTA 5, Grand Theft Auto. This malware never changed. The mod, the malicious mod, is still the exact same one as way back in the GTA implant. So much so, they never changed the strings. Now, I don't mean to do a whole play-by-play from the Discord, but I think there were some pretty interesting components there and a lot of good stuff to kind of walk back this whole investigation, especially the modder or the mod developer himself. At the very start, he had made a statement on his Discord server. This gives us a little bit of insight on the discovery of the malicious mod, and it's kind of wild because, look, this is the developer that's working with Paradox, the Paradox forums and that whole community, but their account is the one that ends up being compromised to push and do and manipulate this mod. But he goes through a couple of different questions here, just asking with like the self-retrospective introspection here, look, hey, was there ever any notification that someone tried to reset their password? No. Was there any notification that someone logged in from a different IP address or a different location? No. No notification or update that the mod was changed, and no notification that it was later removed or disappeared from his account and what they share. This has, rightfully so, led to some scrutiny for Paradox and how the handling of mods and updates and releases and all this could really be improved in terms of security. And it is kind of cool to see some of the conversations in the Discord saying, look, we need to communicate with the mod developer to tell him to check his computer. Hey, make sure he's not infected or compromised, even more so. Eventually, we get to a point where the modder gets to join the Discord and we communicate with them directly. And we get to look back at some of the early breadcrumbs and puzzle pieces that point to the very same conclusion and understanding that we have now. But we could see some forum posts, messages, responses that say, even from the victims and the affected users, look, this is not a joke. They played the game, they had the mod installed, and it emptied their entire software wallet for Exodus. They have the transaction ID, and I'd be very curious about the wallet that it went to if it is the one that we uncovered, but there's nothing they can do. They're totally right. It's crypto, it's not coming back. And I think that's kind of wild because in the moment, while this was going on, that whole idea was just totally dismissed. They say, when we share that screenshot, look, that's not a reliable source. We don't know all the answers, we don't know what we're up against yet, and it's just someone that was turned down. But of course, now that we've uncovered this, we really understand, oh, that is in fact the impact of the malware. But soon enough, we get the developer of the mod himself to join the Discord. I'm sorry, I'm just looking back at the Discord and it's making me laugh. All these elaborate shenanigans, compromising a modder, loading the malware part by part via stack strings, all just to steal crypto. Ooh. They note the IP address has a Minecraft server, ? Running on that port. No, I think that was actually it. That is the default port for Minecraft, though. You're right. All right, I had to scroll through a lot of Discord messages, but we do eventually get the mod developer in the server. They say, aren't you the guy that got hit? And he's like, yes, he is the dev for the mod. And then he says, are you sure if your machine is compromised? He says, unfortunately, yes. Scrolling down a little bit further, this is kind of interesting. We can see the conversations after we share Loch Ness and his original write-up with everything that came up with the Exotickler name. They say, do you know how you got compromised? Discuss the compilation a little bit, but then discusses, it's most likely a stolen password. I don't think the Paradox servers care who or where you are if you have legitimate login and password. Normally websites will do the annoying, we'll send you a confirmation code, but unfortunately that was not the case. They say, was it a stolen password or was it a weak password? Was it maybe from an info stealer, from info stealer malware, or a password from another breach? And he responds, it wasn't obvious. It's not a obvious password, not a dictionary word that you could just find in rocku.txt or whatever, but it's also not completely random, like suggested by a digital password manager. There's a chance that they've used the password before. They couldn't check right now because they have gone ahead and changed all their password, which is a very good thing. Back on the reverse engineering direction, we do get to see another user, Sangiovis. I'm sorry, I think they left the server, but they did see, that profapi.dll is one that is automatically loaded by exodus.exe, and they're tracking that DLL sideloading technique along with potential of the V8 function that are injected. They see the registry key that ends up being created, and even some of the communication while it exfiltrates out to those domains. You did see that was end up being XORed with not hex 33, like the original payload, but it was hex 55 as it tries to hide and mask the Seco seed file that gets pulled out to the external location. I tried to reach out to the mod developer personally. I sent them a DM and asked, hey, can I get your hot take, your perspective, your whole story? But unfortunately, I did not get a response. Still wanted to continue on with this video though, because I'm late already as it is. The Paradox community did share more updates on the incident, discussing a little bit more of the root cause analysis, some of the reverse engineering, everything that we have discussed already and showcased in great detail. But obviously, as you might expect, a lot of the comments that span across however many pages here, 2 or so, users kind of chiming in, look, there are some other potential features or functionality we could implement here to try and make this a little bit more secure for the future. Maybe we could avoid a situation just like this if there are some other opportunities and things to do things a little bit differently. I think there were, rightfully so, a lot of disgruntled users, but there are certainly a whole lot of opinions that are just going to be had from this. And I'll say, I don't know, I don't have all the answers by any means, but I am understanding that it's really hard to try and point blame. And I think at some point, some folks really do want or would like something or someone to blame. And it's hard to say one individual or entity or group or whatever could share some responsibility to try and make things a little bit better. I think there is some opportunity for all of us just to add more security to our own lives. Considering one core component of the story here were passwords or credentials or how a threat actor gained access to the mod developer's account, well, maybe we could track down, was that really a weak password or an insecure password that was leaked or stolen from InfoStealer malware, and Flare could certainly help us out with that. We could just rapidly search for that username or any other, maybe email address, password, or even URL for affected users on Paradox or potentially other leaks, and hey, we could track down a good amount of opportunities for credential access. I don't mean to put anything on blast here, so I'm not going to talk about this much, but I can see, and I know I will redact this, of course, look, there are a handful of passwords that are going to end up being reused, recycled, and repeatedly, even just a small, simple, stupid keyboard walk, or trying to use a standardized password where you'll add simply a 1 at the end, or an exclamation point, or a capital letter at the start. All the things that us as humans will do and make mistakes, but look, I think we could all use a standard password manager and make sure that we won't have mistakes like this just littered out on the internet. So that we can learn from incidents like this how to better avoid some potential supply chain incidents or just have better security. And while obviously not everyone needs to be doing all this reverse engineering that we've been doing to get the technical nitty-gritty details like, oh, binary ninja, x6040 bug, all the functions and peb crawl walk procedure stuff, look, not everyone needs to be spun up on that. But for those of us that would like to, I think it is still part of our responsibility and our duty to, look, make sure folks are informed and all understanding of the impact. With that said, it was incredible to see all of the support and work in the Discord server, and it just warms my heart that folks in the community are willing to do that. Thank you all. And thank you for watching this video. I hope you learned something. I know, my goodness, this was a long one, but I thought there was a lot to cover and a lot of really good things that have some sweet lessons to learn in there. Please do all those YouTube algorithm things, like, comment, subscribe, give some love to our sponsors, link in the video description, and I will see you in the next video.